In the past years, increased carbon emissions from burning fossil fuels for energy has had damaging effects to the environment, like rising global temperatures and ozone layer depletion.
Since a growing economy demands more energy, decreasing energy consumption is not an option, and therefore alternative energy sources like wind energy need to be utilized. Acquiring energy from wind turbines is growing very fast, with global cumulative capacity growing from 59.1 gigawatts in 2005 to 432.4 gigawatts in 2015, and this trend will increase further if better, more efficient wind turbines are developed.
Therefore, we were assigned to design and manufacture a small-scale, horizontal axis wind turbine within the constraints mentioned in the project brief, and with the ultimate aim of maximizing CP at a TSR between 3 and 8. We started our design process by aiming to create something better than the traditional wind turbine blade by drawing inspiration from nature.
Given the low Reynolds number, our initial idea was to investigate the properties of a dragonfly's wing.
We found properties such as the corrugation on the wing interesting. However, due to the difficulties we experienced with modeling the flow around sharp edges, and because such properties would only help prevent separation at high angles of attack, the idea was scrapped.
We then looked elsewhere and found inspiration in the more superior family of animals, the birds. We looked at seagull wings in particular. These have raked wingtips which serve to reduce induced drag. This advantage is evident from its use in the Boeing 787. We estimated that the Reynolds number experienced by the seagull wings during flight are almost the same as those experienced by the turbine at the speeds to be tested.
To have reasonable performance at all test speeds, we decided to optimize the wind turbine for 10 meters per second. We used Q-Blade to investigate the various airfoils. We settled on the SG6043 as it showed a good lift-to-drag ratio at the design Reynolds number of 85,000, which was initially approximated using the tunnel speed of 10 meters per second and the rotational speed limit of 3000 RPM. In other words, this airfoil showed promise at a tip speed ratio of 6.3. The angle of attack at this lift-to-drag ratio was 7.7 degrees, where the lift-to-drag ratio was 52.2. We then proceeded to use the blade element momentum method to determine iteratively the span-wise twist and the chord distribution, as well as the axial and angular induction factors until the latter two factors converged. A tip loss correction factor was also included to improve accuracy. This resulted in an average axial induction factor of 0.53. Rerunning the calculations for different angular speeds revealed a maximum power production at 250 radians per second, where the CP was found to be 0.33.
Structural analysis was performed on MATLAB parallel to the design process and used iteratively to optimize the wind turbine. This was done to make sure that blades do not fail due to the aerodynamic and centrifugal forces experienced.
An initial analysis was done for a simple approximation of the blade, a very simple approximation, by splitting each blade lengthwise into 500 discrete sections and calculating the forces, moments and deflection at each section using beam theory.
The initial results were as expected, with the largest bending moments and therefore stresses experienced near the root of the blade and the largest deflections at the tips. To reduce the stress concentrations at the root, we designed the root to be an ellipse instead of the SG6043 aerofoil.
We decided to design a circular nose and try to make it as small as possible to maximize blade lengths, and therefore design it with a radius of 20 millimeters. To design the shape of the nose cone, we used the Hack series in order to minimize its drag for the given dimensions.
The turbine concept was then made into a CAD model using cryoparametric. The turbine section was created by blending 25 sets of spine points exported from our blade element momentum method script in MATLAB. The root section was extruded into the hub, and between two sections, swept blend was used to ensure a smooth transition.
Finally, we decided to test the model using CFD. We ran a steady-state analysis using the frozen rotor technique in ANSYS CFX, which gave us a similar result. The power coefficient was found using the torque and the angular velocity. This gave us a value of 0.3, which was consistent with the blade element method.
After the design was finalized on Creo, real chord length and area values at the 25 discrete sections was used from the Creo model to perform the structural analysis. It was found the ABS plastic used would not fail under the maximum RPM of 3000, and a tip deflection of 4 cm would be experienced at the tip.
After the design stage, manufacturing begins. By referring to our engineering drawings, the central hub was machined to the desired shape and dimensions in 3 stages: turning, milling, and broaching. The cylindrical aluminum block was first trimmed down by turning. Then, a hole is drilled through the center using the tailstock. A CNC milling machine was then used to give it hexagonal shape. Finally, the keyway was produced using a pressurized broach set, before our group number can be stamped on it. The blade was 3D printed from our CAD model using ABS plastic. The surface of the blade was sanded to remove any rough edges and excess material in order to produce a smooth finish. Finally, the hub was joined to the blade using a single grub screw, and it is now ready for testing.
The next part of the task involved testing the wind turbine that we had manufactured.
This happened at the Donald Campbell wind tunnel, where our wind tunnel was mounted onto testing apparatus which included an electromagnetic brake from which the power generated could be measured. The brake would decelerate our wind turbine to a set RPM range and would record the power produced at very small time intervals, allowing a continuous data curve to be plotted. The wind turbine suffered some problems very early on. The design meant that we needed a very high startup speed, nearly 26 meters a second, which was much higher than the operating conditions it was designed for. Further, the low speed performance of our wind turbine was also poor, and a test could not be conducted at 6 meters a second. The reasons for this will be discussed later. The turbine was, however, displaying very good high-speed performance. At 10 meters a second, approximately 12 watts of power were generated, and at 12 meters a second, around 18 watts of power were generated. When the velocity was increased further to 14 meters a second, the power produced went up to 30 watts. The RPM was also higher than expected at design condition, around 3,800 RPM instead of 2,400. The fundamental frequency was around 4,500 RPM, during which the turbine was very noisy and vibrating heavily. This occurred at around 12 meters a second. When the velocity was increased further, the blade also experienced very large deformations.
The turbine was able to generate power at 12, 10 and 8 meters per second. Unfortunately, the turbine stalled at 6 meters per second. The turbine reached a TSR of 4.79 at 10 meters per second, which was slightly lower than our design assumption of 5. The maximum CP was found to be 0.174 at 12 meters per second, and the turbine has a maximum power output of 18.32 watts. The maximum CP value is approximately 40% lower than our expected value. The two reasons we suspected were first, the lack of twist, and second, the quality of surface finish. Acetone treatment was then applied on the surface for retesting. The maximum CP value increased by 0.01 and the maximum power output increased by 1.1 watts. We think the stall at 6 meters per second could be solved by selecting a different airfoil with lower lift-to-drag ratio, which results in a lower angle of tach and hence higher twist at the root.